Welcome to another Sussex Universe lecture. In this talk we have Dr. Chris Byrnes, who's going to talk to us about possibly one of the weirdest dark matter candidates there is, primordial black holes.
Okay, so thank you for tuning in to another Sussex Universe talk. I'm Chris Byrnes, a lecturer at the University of Sussex, and I'm going to talk to you about black holes and the early universe, and I've subtitled my talk The Dark Universe for reasons which I hope will become obvious very soon. Okay, there are lots of talks online now. There's nearly every Thursday at 7 p.m. a new one is released, and you can follow this web link at the bottom to find all the other talks. Okay, so what is the universe made of? Well, by eye we can look up at the sky. I guess if you're watching this, you probably have done that, and you've seen stars, you've seen the sun, and you've seen a few planets. And we can see that the planets move through the sky, whilst the stars, apparently are stationary, although I'll show you later that that's not quite true. And when we look at them, there's actually, to be honest, not that much we can work out about the universe just with the naked eye. I mean, you could count the stars, you can look at the different colors, you can see where they are, and if you're in a good dark spot, you can also see the Milky Way. So you can see this band of brighter color, which is where there are lots of stars, and that's looking along the band of the galaxy. But how would you know that we're in a galaxy? How would you know there are other galaxies? Well, actually, we simply didn't know until about 100 years ago. So the subject of cosmology, in any form recognizable to what we learn today, is really only a century old, perhaps the time of your great-grandparents. The theory, though, or the underpinnings of the theory, go back a lot further to Sir Isaac Newton, who wrote down what's now called Newtonian gravity right back in the 1600s. And although it's been surpassed, it's still an incredibly powerful and useful theory, and I still teach it today in undergraduate lectures at Sussex. And now it was surpassed, as I said, by Albert Einstein, who came up with a theory of special relativity in 1905, which is effectively the theory of space-time without gravity, and then the full theory with mass involved in general relativity 10 years later and 105 years ago. As great as these two people were and their theories are, they both believed that the universe was static, meaning that the universe wasn't growing in time, it wasn't changing, it was simply an infinite, static, fixed, never-changing universe. And this picture really changed quite quickly after Einstein wrote down his theory, with the discovery that there are so-called island universes, meaning galaxies which are collections of lots of stars, and then a lot of empty space before you get to the next collection of stars which form a new galaxy. Furthermore, and even more shockingly to the two people on the left, Einstein and Newton, was that the universe is in fact growing, and we know that because galaxies which are far away from us are moving away from us. And the further away they are, the quicker they're moving away from us. This is Hubble's law, although Hubble's law was actually written down first by Georges Lemaitre in the 1920s. He was also the first, Georges Lemaitre was also the first to suggest the concept of the Big Bang, where he called it the primeval atom in 1927. And the idea was, because the universe is growing bigger and bigger, if you reverse time, everything must have been closer and closer together. And so at some point, far enough back in time, everything would have been at the same point. And that was the concept of the Big Bang. Now, although I am just highlighting a few people, I want to say that science is always done by much more than a lone genius. It's done by collaborations. In fact, many of my colleagues, some excellent scientists, really don't have any single author papers. And although, yes, it's partly a trend to the modern day that we're becoming more specialized, we're working together in bigger groups, it's nonetheless true that at no point in time was life like a Hollywood movie where it's always some isolated person who goes mad and has the greatest insight, which nobody else could think of. That's not really how science is done. And just to drive that home, there's something called Stigler's law of eponymy, which states that nothing is named after the person who discovers it. And Stigler, of course, was happy to admit that he wasn't the first to write down this rule. And I think there's a relevant quote from Mark Twain. It takes 1,000 men to invent a telegraph, or a steam engine, or a phonograph, or a photograph. The last man gets the credit and we forget the others. These object lessons should teach us that 99 parts of all things that proceed from the intellect are plagiarisms, pure and simple, and the lesson ought to make us modest, but nothing can do that. I think that was true then, and it's, in fact, just at the time of Einstein's special relativity, and it's still true today. Okay, but cosmology then becomes interesting once telescopes were developed, which were large enough and powerful enough to see well beyond the realm of our own galaxy, the Milky Way, into galaxies further away. And by watching how things move, we can figure out how much stuff there must be, and then we learn about gravity, about space-time, because we can start to learn where the mass is and how objects are reacting to that mass by moving. For example, we see the moon. The moon is moving around the Earth, and that is because of the mass of the Earth, which creates the gravitational attraction, which forces the moon to move in a circle. But what would happen if we saw something moving around nothing? And that's not just a philosophical question, it's a very practical one, because that's exactly what we have seen. So if I move on to this video made by the European Space Agency, Space Observatory, sorry. You can see here these white dots are stars, and these are observations taken over many, many years. Let me get rid of the music. And as time passes, the stars move. They move in elliptical orbits, and these blue lines are an artist's impression of the lines that the stars are moving on. And why are they moving in elliptical orbits, even when we can't see any big object in the middle? Well, it must be because there is mass, a very, very large mass, larger than the mass of all these stars moving around it. And the obvious answer is that there should be a black hole in the middle. This is in the middle of our galaxy, and the gravitational attraction of this black hole is what forces the stars to move in these orbits, roughly circular, but not quite, moving around this black hole in the center. Okay. And here is the star which is closest to the center of the Milky Way, and it takes an orbit of about 16 years to go fully around the black hole and back to where it started. And by making multiple observations over more than a decade, this motion has been observed. So although this is a computer image, it's based on real data from real observations taken by very patient people. Okay, so hopefully that gives a clear idea of how, using observations, but without seeing light, we can nonetheless infer the existence of an object. And there's a very long history of doing this. It goes back close to 100 years to the Swiss astronomer Fritz Zwicky, who postulated, right back in 1933, the existence of dunkle Materie, which is the German for dark matter or dark material. And what he did was he observed, using at that time one of the best telescopes in existence, he looked at a galaxy cluster called the Coma cluster. Now, this is a much more modern image, much more beautiful, where we see various galaxies, as well as some stars. And he could observe the relative motion of these galaxies to each other. And he asked, well, how quickly are they moving versus how quickly should they move based on the gravitational attraction between them if all of the gravity is caused by light, meaning all of the stars in that picture image form the forces which move the galaxies around each other and in between each other. And he discovered that there simply wasn't enough material. There must be more, so there must be something dark on top of it. Now, at that time, it was quite a radical idea. It wasn't taken very seriously, also partly because he was a rather aggressive character who made more enemies than friends. But then over decades, people repeated that experiment. They found consistent results, and perhaps more importantly, Vera Rubin and others measured galaxy rotation curves in the 1960s. Okay. So here's an image of one galaxy. Again, it's a much more modern image than she would have had available at that time. And this plot, nicely overlaid on the photo, is the distance from the center of this galaxy, measured in light years, so that's the distance light travels in 1 year. And this is the velocity in kilometers per second, so moving very, very quickly. How quickly around the center are stars, or in this case, 21 centimeter, don't worry what that is, but it's a type of gas, hydrogen gas. How quickly are they moving around this galaxy? And if all of the mass was in the visible light, well, you would have this dashed curve. I hope you can see it. And you see, because there's not much luminous material far away from the center of the galaxy, you would expect the velocity of these objects to decrease as you go further away. But that's not what you found. Instead, the observations showed that, first of all, there was always more matter than expected, and secondly, this matter can't all be concentrated in the center, because the velocity at which these objects were moving around the center kept increasing as you went further and further away. So you can't explain this just with a black hole in the center, even though we know there is a supermassive black hole in the center of most galaxies. There must be additional dark material which extends well beyond the center of the galaxy. And over time, this has been repeated time and time again with hundreds of galaxies. And this sort of curve, which goes upwards or becomes flat rather than decreasing, is always what's seen. So there's a lot of evidence for dark material. Okay. So by the 1980s, about 50 years after the first observations by Zwicky, nearly all cosmologists believed in the existence of dark matter. And how much do we need? Well, the answer is a lot. Compared to the visible matter, the atoms, sometimes called the baryonic matter, you need about 5 times more in dark matter in order to satisfy these observations of galaxy rotation curves and also of the velocities of individual galaxies in the galaxy cluster. If you're interested to know more about the luminous matter, you can watch this talk by Stephen Wilkins. If you want to know about dark energy, which despite the name Dark and Dark is really not connected to dark matter, you can watch this talk by Kathy Romer, both Sussex University talks. Okay, but dark energy came later and it's more controversial. Dark matter was already accepted a good 40 or so years ago. So what is it? Obviously, this is a talk, right, about the dark universe, so what is dark matter? Well, I'm not going to tell you because nobody knows, but based on publications, based on the conferences I've been to, most people have been looking into the idea that it's another particle. It's not part of the standard model of particle physics, but an additional particle with the correct properties that you would need for it to form the dark matter, which we observe indirectly from cosmology, but we don't observe directly if it's a particle. Nonetheless, this seemed like the most likely theoretical explanation, and one promising candidate was through supersymmetry, Okay, supersymmetry is related to, but not directly part of string theory, this sort of search for a theory, so-called theory of everything. And one idea is that for every known particle, there is a second partner particle with a heavier mass, the supersymmetric particle. And if that is the correct theory, then that would naturally give many candidates for dark matter. Unfortunately, though, with the Large Hadron Collider, which you see a photo of here, the super ring in Geneva at CERN, well, it was built at a great cost with two key goals. One was to discover the Higgs boson, which it successfully did. That led to a Nobel Prize for its discovery, but there is no sign, at least not yet, of supersymmetry. Research is continuing, but the motivation for supersymmetry has receded a bit. Another popular alternative is the weakly interacting massive particle called a WIMP. But literally decades have gone by of people flooding underground mines where they search for a direct collision between a dark matter particle and the liquid inside the mine. And why go into the earth inside a mine? Well, it's because dark matter must interact very weakly, as this name suggests. And so you can shield the surroundings from all the normal matter, for example, solar radiation, by going underground. And the dark matter will still find its way through the earth. But very occasionally, you would expect one to bump into one of the atoms inside your detector, inside the mine. And that nothing has been found. Now you might be saying, well, all of this is based on assuming the theory of gravity is correct. And you're correct, but many, many smart people have spent many, many decades searching for alternatives to general relativity, trying to modify it, trying to tweak it, even adding extra dimensions. And none of these attempts have been able to explain or to sort of remove the requirement for the existence of dark matter. It's a very, very difficult thing to do, so most people now would say it's more likely and more conservative to assume that general relativity, at least on large scales, is correct, and that there is an extra component. There's one more piece of evidence I want to share with you about dark matter, and that comes from the oldest light in the universe. And why is there an oldest light? Well, it's because of the Big Bang. The universe hasn't existed forever, so there's only a certain age that anything can have, which is the age of the universe. But light could not travel forever since the Big Bang, because at the very early universe was very, very hot and very, very dense, again because everything was much closer together, so you had much more material in a relatively small area. And until about 400,000 years after the Big Bang, the universe was simply too dense, too filled with atomic particles for light to be able to travel. And so just like looking at the surface of a cloud, there is something inside the cloud, but you cannot see any of its structure. We can look backwards in time from the present until 400,000 years after the Big Bang, and that is the oldest light that can possibly be seen. I should have explained that when we look at something far away, we are looking back in time. That's not a choice, it's a fact, and that's because it takes time for light to travel. Okay, because the speed of light is not infinite. So if you look at the moon, you're seeing the moon about a second ago because it took about a second for the light to travel to us. That's not much, but when you look at a normal star in the sky, it took centuries or more typically for that light to reach us. And why is this important? Well, because when we look at this cosmic microwave background, and here's an image from the Planck satellite, they observed this very cold microwave radiation, the leftover heat of the Big Bang, which has been cooling as space expanded for 14 billion years, and they saw the temperature was almost exactly the same everywhere. There are some slightly colder spots, the blue spots, slightly hotter spots, the yellow and red spots, but the difference is about 1 part in 100,000. So, much, much, much less than 1%. And from these tiny, tiny differences, great galaxies must grow. And they must grow only through the strength of gravity, gravitational collapse. Okay, and they must do that within about 1 billion years, because we can, again, looking backwards in time by looking far away from us, see galaxies which have formed not much more than 1 billion years after the Big Bang. And there's simply no way to do that based on the very small differences in temperature or differences in density which existed at the time of cosmic microwave background, unless you have more gravitational attraction than you think, because you have more matter. And how much more matter do you need? Well, it's about 5 times more. Exactly the same as you need to explain the galaxy rotation curves observed by Vera Rubin, or the relative motion of galaxies inside a cluster seen by Fritz Zwicky. And all of these observations have now been done many, many times by many groups, and they're in broad agreement. Okay, so we need some additional component, non-luminous matter, which must have existed quite shortly after the Big Bang, and certainly before the cosmic microwave background formed. I put this globe up here just to show that this is a projection. This is a projected image of the cosmic microwave background, in the same way that you're used to seeing a projection of the globe, which is, of course, a sphere onto a 2-dimensional plane. One difference, though, is that here we are inside the cosmic microwave background. We're looking outwards rather than with the Earth, where we're looking from the top inwards. So, if dark matter is not a particle, there's only one known alternative. And I think only one alternative, which there could be, and that is it would be a black hole. Of course, people have thought about this before, and the idea originally comes right back from the early 1970s from Stephen Hawking, who sadly died quite recently. And these black holes must have formed early because of this cosmic microwave background. They cannot be the remnants of dead stars, stars which have gone supernova and then collapsed and left a black hole in the middle. Because they do exist today, they could explain galaxy rotation curves, but they cannot explain how the galaxy formed in the first place, or even how the star formed in the first place quickly enough, based on our image of the cosmic microwave background. So could we instead have a so-called primordial black hole, meaning a black hole which formed very shortly after the Big Bang, perhaps a second or less after the Big Bang? And the answer is yes, but we need the initial conditions to be rather different than what we see on the large scales, where our telescopes can resolve the cosmic microwave background, because there we see only tiny differences in temperature, which means that the density underlying this image is very, very close to uniform, and hence there wouldn't be enough gravitational attraction from one region away from another to form a black hole. But perhaps on smaller scales, and potentially much smaller scales, the initial conditions for the universe could have been quite different, and perhaps, sort of violently perturbed enough to form black holes very, very quickly. So what is a black hole? Well, I'll put this very simply. It's something with such strong gravity that not even light can escape from the surface. So to make the analogy a bit stronger, well, if you kick a football up, you see it go up, then gravity, it's constantly, you're trying to pull it back down, eventually the ball loses velocity, it stops, and then it falls back to the surface. If you could kick one fast enough from the Earth, it would go into outer space, and it would never come back. Now, if you compressed the Earth, everything would be closer to the center, the strength of the gravitational attraction on the surface of the Earth would become larger, and you would have to kick that football faster. Now, at some point, as you kept compressing the Earth smaller and smaller and smaller, you'd really have to compress it dramatically. Eventually, there would come a point where not only would you not be alive, but even, if some super being could shine a torch upwards or kick a football at the speed of light and nothing can go faster, it still would not be able to escape. And this is the basic idea of a black hole. It's something with such strong gravity that nothing can escape, not even if you try to escape at the speed of light. You need great densities to do this. To compress the sun into a black hole, you'd have to shrink it into the size of a few kilometers, which means shrinking it by about a factor of 1,000,000. And once you form a black hole, well, you can't see inside it, so a black hole becomes quite simple. A black hole has mass, it has rotation or spin. In principle, it could have electric charge, but in the real universe, any black hole would quickly become charge neutral because its charge would attract other particles with the opposite charge, and quickly it would become, electrically neutral. So beyond that, a black hole has no hair, and hence even if you see a black hole, well, of course we can't directly see, but we can infer their existence, as I showed you, for example, with stars rotating around the center of the Milky Way. We can infer there's a black hole, we can infer its mass, sometimes we can infer its spin. But how do we know how it formed, given that once it's formed, it contains no direct memory of the formation? If you want to learn more about the laws of gravity, then watch this talk by Stephen Wilkins, another older Sussex Universe talk. Okay. So, a bit more about black holes from the Big Bang. They could exist, as I explained, if the initial conditions on very small scales were suitable, if the perturbations were relatively larger. And then, depending on which scale exactly the perturbations were larger, that would set the scale which collapses into a black hole. And potentially they could be very small. They could be light. They could be lighter than the sun, lighter than the Earth, perhaps even a gram or, a very, very small mass. Another difference is that in the early universe, when the density is already high, they could potentially form very quickly and without collapsing by a factor of 1,000,000, unlike the sun. And this gives us one idea of how we might observe the difference between an astrophysical black hole and a primordial black hole, the spin. Okay, so that's why I've got this movie of an ice skater. How does an ice skater make herself rotate? Well, quickly. Well, once she kicks with the foot to start the rotation, she then draws in first the legs and then the arms as close together, and by essentially shrinking her size, then the conservation of the energy associated to the angular motion, the angular momentum, means that she'll spin faster and faster and faster. So let me play this. Okay. Now she sets herself off spinning, starts to draw in the legs, speeds up, draws in the arms, and she's going ridiculously quick, 308 times around every minute, which is incredible and dizzying to watch. And again, think of the sun. To shrink it into a black hole, to make strong enough gravity, you'd have to shrink it from a size of about 1,000,000 kilometers to a few kilometers. So that's a lot of spinning up it would do. And the sun is rotating. It would be rotating a lot quicker if we could pull it in to a black hole. Here's an example of a black hole which has been observed just in the last few years, I think about 2 years ago, from the Vent Horizon Telescope. Now, people are often confused. This was sort of billed in the front page of newspapers as a direct image of a black hole. It kind of is, but of course you don't really see a black hole. What you see is the light of the energy released as particles, as gas, is accelerated very, very quickly by the strong gravity into the black hole. It releases some energy, and some of this light, obviously before it crosses the event horizon, So while it's still outside, some of that can escape. And as the material is heated up, that's quite hot material, and we see that as light. So we're really seeing something like the shadow, a warped shadow, due to the strong gravitational pull caused by a black hole here in the middle. And this was a supermassive black hole. We also see lighter black holes with masses closer to that of the Sun. And we actually don't know how these supermassive black holes are formed. Okay, one more piece of evidence for black holes is the observation through gravitational waves. And this is done using these incredibly accurate instruments, the gravitational wave hunters, which are essentially two arms, which you can see pictured here from a drone. They're about 4 kilometers long each, and there are little laser beams flying up and down in between them, and they are measuring the length of these arms. And the idea is that as a gravitational wave hits this machine, it will make the distance of the arms shrink and expand, because a gravitational wave is a ripple in space-time. It's essentially something which shakes all length scales as it passes through. In the same way that, a similar way to that a sound wave is a vibration of the molecules that make up the air shaking towards you as I speak towards the microphone. Now, gravitational waves are weak. They were predicted, or they're a consequence of general relativity, but it took a long time to detect them. And the detection came only about 5 years ago. So what did LIGO and Virgo see? Here's the third and final movie. It saw two black holes circling in towards each other. And of course it doesn't directly see it. Again, it sees the gravitational radiation of these very large massive objects perturbing space-time and creating these ripples which radiate outwards, which bring out energy, thereby allowing the black holes to move closer and closer together. So I'll play this movie. At the bottom, you see this wiggly line. This wiggly line is sort of the shaking of space-time, which can be observed by these instruments that LIGO and Virgo have built. And this is a computer animation, although it's based on a real event. And okay, this whole thing took only less than a second. It was very, very rapid. It's a very violent event. As these two black holes, one which was about 8 times the mass of the Sun, the other one about 30 times the mass of the Sun, kept circling. They kept emitting radiation that allowed them to keep moving closer together. As they get closer and closer together, the thing gets more and more violent because the distance is smaller, and hence the strength of gravity gets stronger. And eventually what happens is that they crash into each other. The event horizons collide, and that forms a single black hole. And initially it's not spherical, but very, very quickly, in a split second, the whole thing radiates out energy, and then it becomes a black hole with a larger radius, a larger mass, and now rotating. Okay. So these gravitational wave detectors, they've now seen about 30 events. Here's just a few shown in blue. So the vertical axis is the mass of the Sun. So our Sun would be right down the bottom. And it has seen neutron stars with roughly the mass of the Sun up to twice the mass of the Sun. And also black holes shown in blue with masses between about 5 and 50 times the mass of the Sun. This is consistent with what you would expect from astrophysical black holes. So from dead stars, it's only the bigger stars, not the Sun, but heavier stars which can form black holes. On the other hand, it observes primarily black holes which don't appear to be rotating. And this may be a clue that they're not astrophysical, or at least some of them might not be astrophysical, and then say primordial. And this is something I'm working on with collaborators, both a PhD student here in Sussex and someone in Nobel. And watch this space for results, which will come later this year. There's also an idea that perhaps Planet 9, the postulated Planet 9, this is not Pluto, but it's expected again because the motion of Uranus and Neptune is not quite right. Based on our understanding of general relativity, there may be an additional object even further away, and it's been speculated that it may be a black hole, but because it would have to be very light, only a bit more massive than the Earth, it could not be an astrophysical black hole, and if it does exist, and it's a black hole, then it has to be a primordial black hole. And this, if you were viewing this as an A4 page from this side to this side in the portrait notation, this is a one-to-one illustration of a 5 solar mass primordial black hole. Okay, so I hope you've enjoyed this. The detection of gravitational waves won the 2017 Nobel Prize, so this is really an active field. There are lots more observations coming. LIGO and Virgo, so far they've published 13 events, but there are many more in the pipeline. But there's still a lot to discover, and well, what happens in a black hole stays in a black hole. Nothing can come out, so these are difficult questions that we're going to keep asking for a long time to come. And to summarize, we now have very good evidence going right back to the 1930s that most of the universe is in the form of a dark material, and Einstein's theory of relativity remains an excellent theory which has passed all the tests, and many, many very difficult tests for it to pass over 100 years. We still don't know what the dark matter is, but it potentially could be black holes, as long as they formed early enough and hence are primordial. They could explain or at least some of the events which LIGO and Virgo have seen of black hole merging, so watch this space. We don't know if primordial black holes exist, but whether or not they do, the search does teach us two fundamental questions. What is the universe made of, and what happened at the beginning? If you're interested to find out more, you can Google me or click on this link, where you'll see a list of all my articles done with collaborators, done with my students. They've all done great work, and everything is free to view. There's a link to an open access preprint server, so anything which I've published is also freely available. And thank you for watching, and if you're watching this live, there'll be a live question and answer now. Thank you.
Well, we hope you enjoyed this video. Once again, I've got to ask, if you did enjoy it, please give the video a like and subscribe to our channel to see our future updates. If you're interested in the future talks we've got coming up, do visit our website at bit.ly/Sussex Universe. And remember, if you're watching live, the live Q&A starts now at the Zoom link in the description down below.